Okay, so the first thing, we're going to look at motion with some different constants today. The first one we're going to look at is motion with constant acceleration. So we have to look at some things about that. I'm going to give you a couple statements. When an object, let's see, moves with constantly increasing velocity. If I have an object that's moving with constantly increasing velocity, what has to be true about that object? Yes. That tells me it's accelerating. So if you're given words or a description of something, you need to think about that. Then let's think about this. As velocity continues to increase, the distance covered per each unit of time does what? Or fill in the blank. So if my velocity continues to increase, what happens to the distance I'm covering per unit of time, for each unit of time? Increase, decrease, stay the same. Well, somebody said it to begin with. I don't have any idea who it was. Might have been Nicholas or Luke. It seems like it came from that area. Did you say anything? Carter, was it you? Was it Keaton?
Yeah.
What'd you say?
I said
Decrease. So if my velocity is increasing, what is velocity? Meters per second, right? So if that's getting faster and increasing because I'm accelerating, am I going to cover more meters every second or less meters every second? More. So this really should be increases. I can say that velocity increases by the same amount for each time interval, and the distance covered increases for each time interval. So when we talk about all of those things, we should see that we have some relationships happening. I'll wait a minute till you catch up. So when we look at all those things, we can look at the relationships between delta x, v, and acceleration when it's constant. And we don't, I'm putting that there so you'll remember we're talking about constant acceleration. We don't normally write that. So when we look at all of those things, we have a formula that we can use when we're talking about displacement with constant uniform acceleration. and it takes the pieces that we've already talked about and puts them together. This formula that I'm going to give you, oftentimes I'm going to give you three formulas today. We'll probably get through that. Pieces of this formula are subbed in to come up with other formulas. So know that this is like one of this and your acceleration formula are a couple of the foundational formulas, and when I give you other formulas, that's where the bits and pieces of those other formulas come from. So when I look at this, I can say that displacement is equal to 1/2 my initial velocity plus my final velocity times the time over which it occurs. 1/2 BI plus VF multiplied by the time over which the change occurs. Now I think, look at this for a second. Let's look at the first handout you picked up today. It just says honors physics displacement with constant uniform acceleration. Let's look at problem 1. Let's start by reading it. A racing car reaches a velocity of 42 meters per second and then begins uniform negative acceleration using its parachute and braking system and comes to rest 5.5 seconds later. How far did the car travel while stopping? So first of all, what's negative acceleration called? Deceleration. So we're talking about an object actually doing what? Slowing down. So now what I want you to do with that is I want you to take these variables, VI, VF, T, and delta X, and see what you can find in your problem and make your list. Which of those variables are given to you? Do I have a VI? What is it? 42 meters per second. What am I doing in the end? Do I have a VF? 0. And what time does this occur over? I think I read that. 5.5 seconds. So we're looking for delta X. What a surprise, since we just had a formula for that. So let's put our formula down. Delta X equals 1/2 VF, or VI, I'm sorry, plus VF, delta T, and sub in what we know, 1/2. Now I'm going to tell you this right now. My final velocity is 0. 0 makes no difference in the problem, so as you're pulling this down, if you don't include plus 0, that's okay. But you need to be sure that you include everything else. So this would be 42 meters per second, and like I said, plus 0 meters per second makes no difference, and my time is 5.5 seconds. So we get 0.5 times 42 times, oh, somebody's been using this calculator. I would like an answer for delta X in the correct number of sig figs. Yes?
120 meters.
Well, let's see what everybody else gets. What'd you get, Carter? He got 120. Which calculator say 115.5? Yeah, okay. All right, so that is with constant acceleration. My acceleration did not change. Now, we also have to think about, oh, that was displacement with constant acceleration. We have to think about velocity with constant acceleration. And we're going to use pieces of that formula to help us with that. So I'm going to say, when acceleration is involved, it must, this is important, be considered. Every year I have people who like have a problem and there's a variable you're given, especially seems to happen with acceleration or time, and they pick a formula that doesn't include that variable. If you are given a variable, then you have to find a formula that includes all the variables. Why do we have to consider acceleration? Because it affects everything else, right? It affects my final velocity, which is the foundation of what most of the formulas are built upon. So if it's involved, I can say that acceleration can be used to find final velocity of your object. But we must also pay attention to the time over which it occurs. So we have a formula that allows us to do this, and we have a formula that allows us to do this. When I have an acceleration, the formula that I can find or use to find my final velocity looks like this. Vf equals Vi plus At, which if you think about that, that should make sense to you. If I want to know my final velocity, I need to know what velocity did I start with, how much did I accelerate, and for how long did I accelerate. Whoops. So if I want to find my Vf, I have to know my Vi, I have to know my acceleration and for how long the object accelerated. So really, if you want to know final velocity, there are three things you have to know. You know what you probably should do, I didn't tell you to do this to begin with, I don't know where it is. Let's pull out your card and put these two formulas on your card. That one. And if you didn't put that momentum formula on there yesterday, let's put that on there too. I don't think we put that on there yesterday. P equals mv. If you don't have that on there, add it. Delta t takes the change of time into consideration, so this really could be written TF, TI. T is just when they say like 5.5 seconds in the problem. So really there's no I mean, the difference is whether or not you have to do the math to find the change. Sometimes the change is just given to you. And I could write this one as A delta t, we just don't usually. Time is time. What's true about time? Time is money, maybe. What's true mathematically about time when we work these problems? This is important. Yes, it's always positive. You cannot have negative time. If you do, go uh-oh and go back and find out why. Okay, do we have them on our cards? Are you still using them? Gabe? No, you're good. Okay, so the other thing we need to look at is displacement. With constant acceleration. We looked at velocity with constant acceleration. We looked at displacement with constant velocity. When we look at displacement with constant acceleration, we take the first formula that I gave you today and we sub it in to come up with a second formula for displacement. So my second formula for displacement doesn't have any final velocity in it, which is lovely because lots of times I have problems where I don't have a final velocity, and it still allows me to solve because I've subbed in variables for VF. So I can say that delta x is equal to VI delta t, initial velocity over the time in which it occurs, plus 1/2 the acceleration times the time squared. So by using the first formula you got today and manipulating it with our displacement formula, this formula was derived. And that formula can also go on your card. And then I want you to find the handout that says handout 3. It's not the green one, it's the white one right after the green one. And we'll look at that example. Everybody got this one on their card? Okay, so let's look at the example on handout 3. It says, a plane starting at rest at the end of one runway undergoes constant acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What's its velocity at takeoff? How long must the runway be for the plane to take off? Okay, so there's something important about this problem that you need to listen to. When there's a plane on a runway or anything that's taking off, or if it says like a car is entering the interstate, that kind of thing, and when you're given a problem like this, that's essentially telling you that it started from rest. It won't always say starting from rest, the plane, drove down the runway and took off at. You need to infer that it's starting from rest. And that the takeoff velocity is the final velocity because we're talking about when the plane takes off. So given that information, I want you to find the following variables. See what you can find. Let's do VI, VF, A, delta T, and delta X. See what you've got in that problem and then just stop for a minute. Okay, give me a variable, JC. 0 meters per second. Give me the next one, Luke. 4.8. Oh, that's A. Did we have a VF? So that must be a question mark. Do I have a time, Nicholas? $15 seconds. Do I have a displacement? Wait, let's get on the right one, yeah. We should be on the white one. Is there a delta X, Ellie? No. Okay. So, dang, I've got two variables I've got to figure out. I'm going to start, because I like to, with VF first. So let's figure our final velocity. Now obviously, we've got acceleration, we've got time, we've got VI, so that tells me pretty much what formula I can use. I'm going to use VF equals VI plus AT. So VF is equal to 0.0 meters per second plus 4.8 meters per second squared times 15 seconds. See what you get there. Kira, what's VF equal?
72.
She got 72. 72 what?
Meters per second.
Thank you. Is that the correct number of sig figs? Yes, it is. Is that the correct answer? Yes. Good job. So now, did I have to find that to find delta x?
Yes.
Do I have a formula that I can find delta x without VF? Yes, I do. So, let's use that one because it wasn't given to me in the initial problem. Delta x equals VI delta t plus 1/2 a t squared. And I could have a delta here. So then when I plug in what I know, I've got delta x equals 0 meters per second times 15 seconds plus 1/2 4.8 meters per second squared times 15 seconds squared. Okay, I want you to solve for delta x. And when you have an answer, stand up. Okay, check with somebody around you and see if you agree with each other. Who got 36? Who got 540? Why did they get 36? I know! It's the most common mistake made. Don't feel bad if you did it. Forgot to square the time. That gets more people than anything I can think of right now on these tests. So if you square it, you'll have the right answer. If you got 540, you squared it. That is the correct answer. I was actually hoping somebody would get 36, so I could point out not to forget to do that. So what's the hardest part about all this? The hardest part about all of this is when you look at the problem, figuring out which formula do I use? How do you do that? You list everything you know, and then you go to your formulas and you look at each one. You can't just omit a part. Remember that, because people always try to do it. So what we're going to do is break into lab groups, and we're going to finish those two, the green handout and the white handout that's right behind it. Then tomorrow we'll get the formulas for the third one. Okay? And then eventually I'll give you a mixed bag of problems, and we'll see if you can figure out what to do with them. Something to look forward to. Hope you're golfing well, Bianca.